Welcome back. I'm talking to Andrew Johnson about an alternative theory of how the Earth was formed. Now then, let's just go back and look at what the science books say. Tell us about continental drift and how that was considered in the early 20th century.
And this, I think, goes back even to the 19th century. Somebody had observed, that the continent of South America seemed to kind of like be a bit of a jigsaw puzzle that fits with, the African continent. And so then somebody came up with this idea, well, maybe these continents have actually been moving over time, and people said, no, that's ridiculous, because the Earth has always been here, God created it, it's always been like this, it's never changed, so that can't be right. And then there was a chap called, I think his name was Alfred Wegener, in about the early 1900s, I think it was 1912 or 1918. He proposed this idea of what was called continental displacement, and which then was renamed because people didn't like this idea of these land masses sort of moving around. Now, that doesn't happen. And they called it continental drift as a way of kind of ridiculing it, or partly ridiculing it, because displacement is a more scientific word and drift is kind of like, oh, you're just drifting around, don't know what you're talking about, And so there's a bit of language issues used there, and we're all very familiar with how that works, aren't we? But then it was actually, they started to measure this, that the continents were actually moving apart, and you've heard the statistic that, England and America are getting 1 centimetre, or whatever it is, further apart every year. And that was then measured, I think, in the sort of mid 20th century, more or less. And then they thought, oh yeah, the continents really are moving apart, so that's when it's called continental drift. And then they came up with this idea that what's actually happening is we've got this kind of semi-solid inner Earth, or surface layers, and then floating around on the top of that we've got these more solid layers, and that we've got these plates. In other words, the Earth's crust is made up of these plates, and these are floating around, sort of on a kind of the liquid mantle, which is where all the lava and stuff comes from. That's underneath. It comes through the mantle. And that's sort of slightly lower down, and so all these continents are moving around, and that's where we get this idea both of continental drift, as it's called, and plate tectonics. And then I suppose the next development of that was where they looked at the mid-Atlantic Ocean, and they found that on the seabed of the mid-Atlantic Ocean, they'd found these ridges, these hardened ridges of essentially lava that had solidified over hundreds of thousands of years, and basically there was this spreading, the ocean floor spreading. It was spreading from this central fault line, which was volcanically active, and they've sent submarines down there and filmed all the volcanic vents, and there's various things going on down there. And then they were also able at that time to measure the age of this ocean floor spreading, and measure how quickly it was happening, because what they observed in this rock, there were ferrous materials which had become magnetized due to the Earth's magnetic field, and they noticed that this magnetic field had flipped. I forget the exact figure, but every so many tens of thousands of years, or hundreds of thousands of years, and so they're able to age how old these parts of the seabed were. So this is one of the key studies that was started in the 1950s, and they did various surveys around the world and looked at the ocean floor, and they measured the age based on these magnetic field reversals. And the very peculiar thing that came out was the oldest ocean floor that they could find was dated to around about 180 million years. So even if you go right to the coast of America, the east coast of America, or the western coastal parts of Europe and Africa, the oldest ocean floor is only 180 million years, whereas the age of the Earth is estimated to be about 4 billion years old, according to all the geology textbooks. So that presents you with a bit of a problem, because the ocean floor is much newer, by hundreds of millions of years, than the rest of the geology on the planet. So then they sort of said, well, if these ocean floor is spreading, and we've got the continents moving apart, then what must be happening somewhere else that we can't see is that the continental plates must be going under another of the ocean plates elsewhere on the planet, because then the ocean floor stays the same size and the Earth stays the same size, and what we're getting is subduction. And so the continental plate is being forced under either another continental plate or under an oceanic plate.
So this is a generally accepted geological phenomenon called subduction.
Subduction, correct.
Right.
That's one of the key things.
Which really is a theory.
It is essentially a theory. Now, they'll claim that there's certain evidence for this in the Far East. And they say that there's subduction going on in some of the areas there, and they can prove that this is where the continental plate is being destroyed because it's been subducted under another plate,
Right.
and it's going back down into the lower areas of
Right.
the Earth.
So let me interject there. So they're trying to explain the phenomenon without having to say that the Earth is expanding.
Yeah, essentially.
Right. Now let's just look at a few other areas that have geologists or I don't know what you'd call them, paleontologists scratching their heads, and that is finding things that should belong at the bottom of the ocean on the top of mountains, such as fossils, and also the physiology of dinosaurs.
Yes.
Just
yes.
tell us about that.
I mean, everyone knows, everyone's taught at school, you know, probably in primary school, that dinosaurs were huge creatures. You know, there seems to be good evidence for this because we have skeletons, you know, and they've reassembled these, and they're in the Natural History Museum, and they're huge. You know, the Brontosaurus. You think, wow, these things are amazing, and you're fascinated as a child by these things. But then, you know, when you start to look at this, you think, well, hang on, if this was at least a bit like some of the creatures we have now, then how did it live? Because, for example, if you calculate the required pressure to pump the blood from the animal's heart up to its head, you know, the heart would have need to have been so big, you know, it wouldn't have had anything room for anything else in its body almost, you know, because of the pressure that you'd need. But even I think more simple to calculate is things like weight ratios. If for example you calculate the surface area of the foot on the ground, and then you calculate the weight that foot has to support of the animal, as you get bigger and bigger, you find that the dinosaurs' bones and feet and so forth could not have supported the animal's weight based on the force of gravity that we have now. So if you do the calculations that you say you would do for an elephant or a giraffe or something, the dinosaur is no longer viable. And the problem becomes even more severe for the dinosaurs which flew, because the problems that you have there is that, you know, power to weight ratios, wing surface areas and that sort of thing, they're much more extreme than for land animals where you're dealing with, you know, mechanics and mechanical areas and that sort of thing.
So that whole observation suggests that the force of gravity was possibly less, say, 100 million and more years ago.
Correct.
Right.
Correct.
Now, what about oceans then, and things that are found in areas perhaps where they shouldn't be? Tell us about that.
Well, of course, that's another interesting area. I mean, I remember being set this question in geography, or this question came up in geography class. Where did the oceans come from? You know, you read the textbooks about the dinosaurs, for example, and they all say, in the time of the dinosaurs, there were no deep oceans, only shallow seas. So one of the big geological mysteries is where the deep oceans came from. How did we get those? And that's not really explained very well. You'll hear, for example, talk of, well, there's two problems. One is how come the oceans are so deep, and the second problem is where did all that water come from? And, you know, people will say, for example, that comets, the water came on comets, these balls of ice which were in the primordial solar system, and we had hundreds of thousands of these comets crashing into the Earth, and they brought all the water. But that doesn't really, if you forgive the pun, hold water when you start to look at all the problems with that theory and the volumes and so forth.
So some people have put forward that if Earth's gravity was less in the days of the dinosaur, going by Isaac Newton's gravitational law of gravitation, F equals J/m over r squared, they say that, well, the Earth must have been less massive.
Correct.
To have a less gravitational pull on
Correct.
the dinosaurs. So therefore, they come up with the theory that the Earth is not only being expanding over millions of years, but actually gaining mass.
This is one of the, this is
more
what
stuff has been added to it somehow by
Right.
some magical process. And am I right in thinking that both James Maxwell and Neil Adams, they both support that view?
Correct. That's one of the key issues that when we get onto Peter Woodhead's ideas in more detail in a few minutes, that's one of the sort of nubs of the problem. That James Maxwell, who has done a lot of geological research, which to me at least proves that the Earth must have been a different size in the past. It must have been smaller. Right. As you say, he thinks the mass was also lower and the mass has increased. So we've got this extra mass which has made the force of gravity now much stronger than it was in the time of the dinosaurs.
Right, and that's where Peter Woodhead comes in.
Yes.
Because he says, no, the Earth's mass has been constant,
Correct.
but it has been expanding. And we'll explain how that works after this break.